I have started the recording. I recorded the last time we were studying threads, right? And we created multiple threads and we shared a global variable between those threads, counter, and basically the two threads that we had created, they both were incrementing the counter by doing counter is equal to counter plus 1. Okay? And they both were incrementing the counter 10 million times. But when we compiled and ran that code, we saw that our expected output that should have been 20 million, the final value of the counter that we were printing in the main thread, it should have been 20 million, but instead it was not 20 million. Okay, so I had said that we will in next classes we will discuss why this is so and why it is not 20 million. So I recorded the rest of the lecture on the video, and a couple of lectures after that, the next chapter on locks, and I had uploaded those videos on YouTube. So how many of you guys have been to YouTube and you have seen the videos? You can raise your hands. One. Others? Hmm. 1 out of 38, 40 is not a very encouraging sign. So in asynchronous, in these online sessions, we will try to use synchronous sessions for discussions. Okay, so that's why I uploaded the videos online on YouTube so that you guys can see and try to understand what I was saying in those videos. And if you do not understand anything, any particular thing, you can basically write a question, a pinpoint question about one particular thing, and we can ask in these interactive sessions. I can explain those problems to you. These topics are important. Multi-threading and synchronization between threads. It is an important topic, and you guys will be like not only will there be assignments and question in the exams about these topics, but also when you later go into professional life, uh, whether it is in interviews or on real job tasks, you will be needing these concepts. Okay, what is multi-threading? How can we use multi-threading to improve the performance of our program, and what are the problems that arise when multiple threads share global data? Okay? So please uh, go to YouTube, watch these lectures, and if you have any questions, ask me in these interactive sessions. So right now, since you guys have not seen the videos, we will not be discussing those videos in the class because that is your job to see those videos when you have time. And instead, we will go ahead and we will discuss another topic from the last section. If you remember, in the last section, we were doing paging, and we have reached at a point where we had said that paging is extremely slow. Okay, so there are remedies that the operating system and processor makers have invented to work around the slowness of the paging policies, so that the performance of a program does not degrade too much. Okay.
Before that, sir.
Yes, please.
Yes, sir. Sir, I think you saw that we had mentioned it in the team's comments that it was very difficult for us to complete the assignment by the deadline. So please consider extended the deadline, sir, because we don't know any idea about the syntax or how C language works, or we haven't done anything related to system programming either. So can you please consider to extend the deadline of the
Before I
assignment?
consider your question, I'll try to answer your arguments that you have proposed. You have said you do not have any experience doing C programming. Okay, you don't do C programming. But to my knowledge, in GIK, right from the first semester, you guys do C++. C++ is a superset of C, okay, 99% of the time. So if you guys know C++, which I'm sure you have done in more than one courses, C, this excuse that you don't know how to program in C, this is not very credible. What is the thing that is in C that you have not done in C++?
There is a lot of difference between C and C++.
Please
Like we
explain.
can, like sir, we cannot directly allocate dynamic memory in C. C we have to use functions, and C++ we can directly allocate dynamic memory, and there are no classes, no object
Give
oriented
me.
concepts in C. In C,
No,
so
no, no,
sir, how
no, no,
do you
no.
expect that?
Oh, you are telling me what you can do in C++, but not in C. I'm asking about what is in C that is not in C++. You said you cannot allocate dynamically memory in C. How do you do allocate dynamic memory in C++?
Malik,
No, in C++.
sir, a new keyword use करते हैं.
No, no, I'm asking the person who had raised this question.
Okay.
Sir, we use new keyword.
New keyword, okay? So
Yes.
in C, how would you do it?
Sir, we do it with malloc functions.
Malloc. Okay, so new is also a function. Like in the background, there's a function called, and malloc is also a function. So
Sir,
in both
sir,
languages, you.
that's
Oh,
sir.
let me
Yes,
finish.
you are right,
Let
but
me
that's a difference
finish
that
first.
there.
Let me finish first. So in both languages, you call functions to allocate dynamic memory. Both memories, in both functions return pointers to you that then you use to access dynamic memory. Okay. Now tell me what is the difference.
Sir, this is just one word, new and malloc. There are lot many functions which we do not know, which we do know in C++, but we do not know their alternative in C. So
Give
this
me an
takes lot
example.
of research, sir.
Give me an example.
सर इसमें
Oh,
जो सिस्टम कॉल
let
है सर.
let that person speak. I will come to you later.
Yes, sir.
No, no, the person who was saying that there is a difference in C and C++. Please
Sir,
give me an example.
सर सर बहुत सारे एग्जांपल्स हैं सर. अब हम आपको सर कैसे बताएं कि कितना डिफरेंस है, क्योंकि हमने तो ट्राई किया ना सर, हमें तो बहुत ज़्यादा फर्क नज़र आया है.
I'm sorry.
सर वो
Next,
लाइब्रेरीज का भी वो है मसला है.
let me come to that. Let me come to that. So the other point originally was that you have not done any system programming. Okay. So in this uh, assignment, the functions, system programming functions that you are going to use are fork and exec. Okay. And fork and exec I have covered in my initial lectures line by line. I have explained their working in detail. Every argument, what does it mean, and how you can use fork and exec to create new processes. Okay. And also, if I remember correctly, we had done one example at least where you can redirect the output of the process that you have created. It is all in the book, the examples. You only have to follow the examples.
Sir,
Yes.
some of the libraries that they've used are not available for Windows. So we'll have to do like
Exactly,
we have,
sir.
Which
no, but
libraries?
let me
Which
finish.
libraries?
There's
Sir,
something
things
called
as
UNISTT.h. It doesn't
an
work for
SYS
Windows
and
function.
SYS.
And there's also for that I found a substitute. It's called process.h, but there's some other libraries that did not work. I don't know
Okay,
their name.
so let
And
me answer
so
answer. Let me
yeah,
answer this question first.
one more
Let me
thing,
answer
sir.
this first.
So
Let
that's
me answer this. So these system calls that we are studying here, they are for Linux and Unix. Okay, so you guys to need to have access to some Linux Unix type systems to do this assignment. So if you try to do it on Windows, of course you will run into problems because Windows uses different system calls compared to Linux or Unix. So one workaround could be in all Windows 10, I think there is a subcomponent called Windows Subsystem for Linux, WSL. You could use that to open that and then use install GCC in that Windows subsystem for Linux, and you can have access to Linux system calls in that module inside your Windows. Okay. Another option could be you install a virtual machine, and inside that virtual machine you install Linux. Okay, and in that Linux you do your programming. That is second option. A third option, you can Google. There are online websites that give you access to Linux online in the browser. Okay, so you could use Linux in your browser on Windows to write code and compile it online, and then copy that code and submit it. Okay, so if you're doing it directly on Windows, that's a wrong approach.
Sir, can you please give me a second, sir?
Please go ahead.
Sir, the thing is कि यहाँ पे ना whatever thing that we may raise, जो भी हम बात करें, you're obviously going to give us solutions for that because you already know what that is ना, because you already are a connoisseur of that and we know कि आपके पास उसके जवाब हैं. We are not saying कि it's not possible. All we are saying is कि it's a very intuitive and it's a very nuanced assignment and it requires, if you want us, अगर आप चाहते हैं कि हम सिर्फ सबमिट कर दें, हम लोग जिस तरह अभी आप सॉल्यूशंस दे रहे हैं, आपको सॉल्यूशंस पता है, हम लोग एक दूसरे से करके और जल्दी जल्दी में वी कैन डू दैट बाय 12 o'clock कि हम लोग सब जो है बगैर समझे हुए आपको असाइनमेंट सबमिट कर दें. बट इफ द पॉइंट ऑफ ऑल दिस इसके ये जो सारी बातें आपको पहले से पता है, सिंस वी डोंट नो देम, अगर हम इनको सीख के कर लें, अगर इफ वी ट्राई टू अंडरस्टैंड व्हाट दीज थिंग्स मीन एंड व्हाई दीज लाइब्रेरीज आर नॉट वर्किंग, अगर हम इन चीज़ों को समझ के करें तो ये 12 बजे तक, मतलब इट्स नॉट गोइंग टू बी डन हमारी डेडलाइन तक. तो आई वुड रिकमेंड, आई वुड रियली वांट टू, आई मीन आस्क इट कि अगर आप चाहते हैं सर कि, बिकॉज आई वांट टू लर्न इट, तो हमें थोड़ा सा ज़्यादा टाइम दे दें ताकि हम इसको समझ के कर लें rather than just doing it for the sake of doing it.
Acha, I'll again go point by point. You said it's a very nuanced and something assignment. It is not nuanced at all. It is just understanding the example in the book, copy pasting the code, slightly tweaking it, and then you would be done. Okay, it's not like there's no complicated or nuanced detail in this assignment. And the second point that you raised was that yes, that you could all submit it without understanding it. I have written in the assignment that you guys could be called for a viva. Any of you randomly I can choose, and line by line you will have to explain every single line of your code. Okay, so that might or might not work depending on the random person chosen for the viva. Okay, and the third point was, what was the third point? Yeah, that I know and you don't know. I already know. That's why I have the solutions and you guys don't know. Regarding this point, all these points, I think the first query that I have received about the assignment, it was last night on an email, okay, that I replied this morning. So if you guys start working on the assignment the evening before the deadline, then of course you are going to have the problems. If you guys had started early, I had written an assignment to start early, okay. If you had started on the first day, you would have realized all these problems earlier and you could have contacted me earlier and you could have, I mean, either an answer from me or you could have found a workaround by searching on internet yourself how to solve all these problems. So if you guys start on the last evening and then you say that the deadline is unrealistic and we want to learn it, but you are forcing us to submit it without learning it, this I think is slightly unjustified. I will agree to you guys. I will extend it if you want, but only for a limited amount of time. How much extension do you guys want? Hello?
Sunday.
तो संडे तक कर दें.
Okay, I will do it on Sunday until Sunday, but this is like the first and last extension that you will get from me. There will be another assignment because if you realize that we have limited time until the finals. If you are pushing the deadline of this assignment, you will be getting less time for the next few assignments. You guys realize this, all right? Hello, an answer would be nice.
Yes, sir, we do understand that.
Yeah, so there will be another assignment on programming. It will be on threads and synchronization, etc. The topics that we started last week, and of whose videos I have uploaded. For that, I'm afraid there won't be um, such extensions. Okay, I will give you a week's time for that assignment also. Okay? And if you guys start earlier, you will be able to do it within the week. But
Sir,
if you
excuse me, sir.
wait a minute. If you guys repeat the same thing, that if you start on the last day or just before the last day, and again you come up asking for an assignment extension, sorry, I'm afraid I will not be able to grant it. Okay, so you have asked for until Sunday. I will give you until Sunday, and I have already made clear the implications of this extension, that you will be getting less time for the next two assignments. Okay, so if you guys accept all these conditions, you have the time till Sunday. You can. This assignment, by the way, is not difficult. I think an average student should be able to do it in one day, like 7-8 hours, even if they have not done a lot of C programming, system programming. Just by going through the relevant chapter of the books, understanding the examples, typing those examples in the code, running the editor, running them, compiling them, running them, and see how they work, and then slightly modifying the code to achieve the assignment's goals. So okay, I'll give you until Sunday. What were you saying? Somebody was saying something.
Sir, हो गया हमसे.
Okay. So I will give you until Sunday. So the submission will be on MS Teams. Okay. You will submit one file, the code.c file, on MS Teams. Okay, and the name of the file should be including your reg number as it is mentioned in the assignment document. Is it okay?
Yeah, it's completely fine, sir.
Okay, so after this class, I will extend the assignment deadline on MS Teams. So if there are no further assignment related questions, I will go ahead and open those slides that we were discussing a couple of weeks ago. The chapters, the video that I have uploaded on threads, synchronization, and locks, etc., that I am not going to repeat telecast in the synchronous lectures. Okay, so you will have to go watch those videos and come prepared for the synchronous lecture next time. And meanwhile, I'll also upload further videos about the next few chapters. So this time we'll go back in time and start or finish about the chapter that we had started about paging. So let me share my screen with you guys. So can you guys see this screen?
Yes, sir.
Okay, good. So we had studied how a paging scheme is implemented. Paging basically gets rid of external fragmentation. There might be some internal fragmentation due to paging, but for the moment we are ignoring it. And the main problem that we were facing in paging scheme, there were two problems. One, that paging was very, very slow. Okay. And second, paging uses page tables, and page tables occupy a lot of space in RAM. Okay. So we'll see how these two problems are solved in the next few minutes. But before we move further, just for repetition, I think I asked this question in last week also. Somebody replied, so some other person may reply. Why is paging slow? Just to repeat or revise, paging is used to translate virtual addresses into physical addresses. Okay, but paging, we are saying, is extremely slow. Why is paging slow? Why was paging slow? Somebody please.
So it requires two memory reads.
Because it requires two memory reads. Very good. And what are those two reads? I mean, why do we need two reads?
One is to get the virtual address and then one is to get the data, I guess.
No, the virtual address is generated inside the processor.
Mhm.
Okay, so when you say one is to get the virtual address, this is
I
not
mean the
technically correct.
physical. Or
Yeah, go ahead, go ahead. Go ahead, you are on the right track here.
um,
In the paging scheme, what do we need to translate the virtual address into physical address? Okay, before that, in the paging scheme, what is a virtual address composed of? What are the two informations we have inside a virtual address? Two pieces of information. See, you guys have like forgotten, but you see, a virtual address is composed of a virtual page number plus an offset. Okay, it's a concatenation of virtual page number and an offset. So if we want to translate this virtual address into physical address, what information do we need? No, this kind of silence is not healthy at all.
Offset.
No, the offset is inside the virtual address. Okay, there's something which is not in the virtual address that we need so that we can convert this virtual address into physical address. Yes, please. Oh, this is very discouraging situation. In the virtual address, we have the virtual page number and the offset. Okay? This is the virtual address of, let's say it's a virtual address of a data. Where is that data stored actually?
Page table.
Page table store data or something else? What do page tables store?
Memory address.
Memory address is not exactly correct, but memory address of what? What did you want to say?
सर वो virtual जो होता है सर.
क्या होता है?
सर virtual memory address.
No. Virtual memory address is not inside the page table. No, page tables do not store virtual memory address. Virtual memory address is generated inside the processor, let's say by the ALU, and we have to, and MMU receive this virtual address, and the job of the MMU is to convert this virtual address into physical address and send the address to RAM so that we can read data from the correct location in RAM. Okay, so virtual addresses are not stored inside the page table. Virtual addresses are generated by the processor, and then we have to convert this virtual address to physical address to get the actual address of the data in RAM. Okay, this situation is bad. Okay, just because you guys don't ask any questions and I don't receive any queries about these topics outside this class, the impression was that everything is perhaps going well, but it is not. Okay, and I would like to emphasize here that it is your job to update yourself. The ball is in your court. It is your like responsibility, duty, or whatever to open the book, read those chapters, watch the videos that we have uploaded so far, use Google or whatever tools to understand the content of the chapters of the book. If the situation is like this, the way I'm saying it right now, if it continues like this, then I'm afraid it is going to be bad in the exams, quizzes, etc. Okay, so please take these things seriously. And right now, most of you, like 95% of you, are totally blank about all the questions that I am asking. So I'll repeat summarily what we had done is in this chapter, and I expect you guys to catch up on your own in your free time by reading the book chapters. Yeah. So in paging, basically we divide the virtual address space into virtual pages. Okay. So virtual pages, here we have, no, this is a physical RAM, but let's say we have a virtual address space which is of 64 bytes. That's our example. We divide into pages, each page is of 16 bytes. So that virtual space would have 4 pages in it, okay, because 16 fours are 64. Those 4 pages, they will comprise the 64 bytes of the address space, and every byte of the address space would have a virtual address. And since it's 64 byte address space, the virtual address in this address space would be of 6 bits. And this virtual address will contain the information about the page in which that byte is located, as well as the offset within the page for that byte. So out of those 6 bits, 2 bits will be used for page number, for the virtual page number, to tell you which virtual page this byte is located in, and the rest, the 4 LSBs, will be used for the offset of that byte within that page. Okay, so once we have those virtual pages in virtual address space, we can divide that virtual address space into pages, and those pages could be placed independently in the physical RAM anywhere. Like here we have physical RAM of 128 bytes. So if we want to place the 4 pages of the virtual address space discussed in the previous slide at different locations in RAM, because operating system can move memory anywhere it likes in RAM, we would place it like this. We will basically divide the physical RAM into blocks whose size would be exactly equal to the page size, virtual page size. Okay, so the division of this physical RAM, we call each unit a page frame. Okay, so each page frame is exactly of the same size as a virtual page. Okay, just like we had virtual pages of 16 bytes, similarly we will divide our physical RAM into chunks or sections of 16 byte each. Okay, and these chunks of 16 bytes, when we talk about physical RAM, we would call it a page frame. Okay, so virtual address is divided into pages, and physical RAM is divided into page frames. And then the operating system can choose to place the virtual pages into any of these page frames. Okay, since the size of a page frame is exactly equal to the size of the page, they can be moved anywhere. So this is an example where we basically placed our 4 virtual pages into 4 page frames in this physical RAM. Okay, the physical RAM had 8 page frames. Out of these 8, 4 were used to store the virtual pages of the virtual address space. Now, since we have placed these virtual pages at different locations in RAM, the data of these pages would be stored in these page frames of the RAM. If we have a virtual address of a byte in the virtual address space, it would be composed of page number and the offset within that page. This is the virtual page number and offset within that page. But that virtual page has now been placed in a physical page frame. Okay, just like page 1, virtual page 1 has been placed in page frame 7, page 2 in frame 5, page 0 in frame 3, and page 3 in frame 2. So if we have a virtual address containing the virtual page number and the offset, we need to find its corresponding physical address. Okay? And for that, we need the information about where this particular page, virtual page, has been stored in RAM, in which page frame. Okay, so this virtual page has been stored in which page frame? For page 0, it's stored in frame 3, page 2 in frame 5, page 1 in frame 7, and page 3 in frame 2. Okay? So once we have this information, we can convert this virtual address into physical address. Okay, and the conversion from virtual to physical address is very simple. In virtual address, you have the virtual page number and the offset. Okay? To translate the virtual page number into virtual address into physical address, we need to find the physical page frame where this virtual page has been stored. Okay, and once we have the physical frame number, we can just replace the virtual page number by this physical frame number and keep the offset as it is. Okay, this will give us the physical address of the virtual address. And this translation or this mapping between virtual page number and the physical frame number to keep track of which page is stored in which physical frame, this is done by the page table. Okay, so the page table contains mapping between virtual page number and the physical frame number. So it's a table whose entries contain the physical frame number and whose index is the virtual page number. So here in this page table, I have 4 entries. So the entries have indexes from 0, 1, 2, and 3. Okay, so these indices are virtual page number, and the value at that index, the value at each index is the physical frame number. Okay, so it's a mapping between virtual page number, which is the index, and the physical frame number, which is the value at that index. Okay, so this mapping is telling me that page 0 is stored in frame 3, page 1 is stored in frame 7, and page 2 is stored in frame 5, and page 3 is stored in frame 2. Okay, so page table contains these mappings. So once we have the virtual address, we extract the virtual page number from that address, and then we go and look inside the page table to find the corresponding frame number for this virtual page number. So since it's a mapping, so we go and look at the index 01, it's a virtual page number. So in this table, the virtual page number are the indices. So 01 is this second index. For the second index, it is telling us that the virtual page number 01 is stored at frame number 111, which is 7. Okay. So we will translate this virtual page number into physical frame number and keep the offset as it is, and this will translate our virtual address into physical address. Okay. So page tables contain this mapping. So now coming back to my question again, why is paging slow, and why do we have to access memory twice, as your friend said?
सर एक दफ़ा वो इंडेक्स वाला काम करने के लिए
वो इंडेक्स वाला काम क्या होता है? यूज आई मीन
हम सर वर्चुअल एड्रेस से हम मतलब इंडेक्स लेके उस वाले पे जाएंगे जो मेमोरी में उस वाली पेज पे मतलब वो जो पड़ा है वो लेके फिर उसके बाद कन्वर्ट करेंगे, मेरा ख्याल है।
नहीं, ये ख्याल ठीक है. If you could just explain it in proper words. The idea is right, correct? So let's say we have a virtual address. I will go directly to this diagram. Before I go, I'll just explain what your friend said. You have a virtual address, okay? So you need to read data from that virtual address, but that data is stored in RAM. RAM has physical addresses, not virtual addresses, okay? So before you access RAM to read that data, you need to convert this virtual address into a physical address, okay? And this virtual address is composed of virtual page number plus offset. To convert it into physical address, you need the physical frame number, okay? And that physical frame number is stored in the page table, and that page table is stored in RAM, okay? So to convert this virtual address into physical address, we need to read the physical frame number from the page table in RAM first, okay? So we need to access RAM once to get the physical frame number from the page table, okay? So once we have read that physical frame number from the RAM, our MMU will convert this virtual address into physical address, okay? Just like I showed you in the slide a couple of minutes ago. So we have converted the virtual address into physical address, and we have had to access RAM once for this conversion, okay, to read physical frame number from the page table. This is one RAM access. And once we have converted the virtualization to physical address, now we need to go into the RAM and read our actual data. Okay, so this will be the second access that we will have to make. That's why in paging, if we don't do anything, we have to access RAM twice for every memory read. Once we need to access RAM to get the physical frame number from the page table for virtual to physical address conversion. And then once we have the physical address, we need to go and access RAM to read our actual data. Okay, is this clear?
Yes, sir.
To others? Is there anybody else present? Okay, if this is the attitude that you want to continue with, I have no issues. And I mean, the loss is yours, because in the end, you will have to do the assignments, pass the vivas, do the exam, etc. So we'll just move forward. So if we have to access RAM twice for every memory read, it will make our programs very, very slow, because RAM access is very slow compared to the speed of the processor. So to see a practical example, we have this example code. We have an array of 1000 integers, and we have a loop which is initializing each element of this array by the value 0. Okay, so this loop, it will be converted to this assembly, this set of assembly instructions. Okay, so this is a for loop written in assembly, and if we explain it line by line, these addresses in this column are the addresses where these instructions are stored in RAM. Okay, so these will be the value generated by the program counter to read these instructions. And then we have these instructions which are basically move. You guys know move is it moves data from memory to register and register to memory. Okay. So here it is basically moving this value 0 to this address. Okay. So what is this address? This is basically the address of the array element array I, which has been calculated by using the technique that you guys know already. This is a register which contains the base address of the array. Okay, base address basically is the starting address of the array, and this is a register which contains the index, the current index, which is I, and then we have a third argument, which is basically the size of each element of the array. Okay, so if you are giving this size of each element, which is 4 bytes, and the index and the starting address, you can calculate the address of each element of the array. Okay, so you guys know this technique already, that each address, given this information, the address of each element of the array can be calculated by base plus index multiplied by size of each element. Okay, so this will give us the address of each element of the array. So what this instruction move is doing, it is basically moving this value 0 to one element in the array here, depending on the index I. Okay, the base address and this size will not change, but the index I will change during the loop. So little by little, it will access each element and store 0 in each element in the array. Okay. So in the start, I is 0. So this will be base plus 0 multiplied by 4, which is the base address, which is the address of the first element. So it will move 0 to the first element of the array in the first iteration. And then the next line is increment ex. Ex, as we saw, is the index I. So for the next iteration, we are incrementing the index I. And then it is checking the loop condition to see whether we have reached the end of the loop or not. So it is comparing this index I to this value 0x03E8, which is the value 1000 in decimal. Okay. So it is comparing this value, and then the next instruction is JNE jump not equal. So if the comparison has found that the values are not equal, then this instruction will jump to this address. Okay, 1024. 1024 is this starting instruction address. Okay, so it is basically going back to do another iteration of the loop. Okay? And it will continue to do so as long as this index is less than 1000. Okay, and once this index is equal to 1000, then this jump not equal will see that it is equal and not equal. So it will not jump back, but it will move forward. Okay, and our loop will end. So every iteration I is changing, and based on the value of the I, this address calculated here will be the address of the next element of the array, and this instruction will store 0 in the next element of the array. Okay. So if we have this code and this data stored in RAM, then our physical, will have virtual addresses for the code and this array, and they will be converted to physical addresses. So virtual address will contain the virtual page number and the offset. And the physical address basically will be generated by converting this virtual page number into physical frame number and then concatenating the offset. Okay? And all this information, the mapping between virtual page number and physical frame number, will be stored in a page table. Okay? And the page table itself would also be stored in RAM, okay, at some physical address. Here it is. When the loop runs, okay, so what will happen is program counter will generate the instruction addresses. We will have to read those instructions and then execute those instructions, okay, because those instructions are in RAM, so you have to read those instructions. But those instructions are in RAM, and the addresses generated by the program counter are virtual addresses. So to read those instructions from RAM, we'll have to convert these virtual addresses into physical addresses. And for that, we'll have to access page table. Okay, so even for reading those instructions from RAM, we'll have to access RAM twice. Once to convert the virtual address of the instruction to the physical address to get the physical frame number from the page table in RAM, and once we have the physical address, then we'll access RAM a second time to read the actual instruction. Okay? So this is what this table is showing. So for the move instruction, it will have to first, this is basically showing the graphs or data for memory accesses for each instruction. So for the move instruction, first we have to read the move instruction to execute it. So to read the move instruction, we need to get its physical address from the virtual address. To convert the virtual address of move instruction to physical address, we need to access this page table. Okay. So once we have the physical frame number, we'll convert the virtual address into physical address, and then we'll actually read the move instruction. Okay, we'll access the code section and read the move instruction. Okay, so reading move instruction has required us two memory accesses: one to page table, this gray dot, and one to code segment, this black dot. Okay. So once we have read the move instruction, we'll execute it. So executing move instruction, what is move instruction doing? If you see here, move instruction is storing data into array element. Okay, so this address of the array element, it is again a virtual address. So to store array 0 in this array element, the move address will have to convert this virtual address of the array element into physical address. So you see, during execution, move instruction need to convert this virtual address of the array element into physical address. So what it will do is it will get the physical frame number for the array from the page table in RAM. Okay, so it will access RAM during its execution to get the physical frame number for the virtual address of the array element. So once it has the physical frame number, it will convert the virtual address of the array element into physical address, and then it will actually go ahead and write 0 in that physical address. Okay, so move instruction during its execution will access RAM twice to store 0 into an array element. Okay, so once to access the page table to get the physical frame number so that it can convert the virtual address of the array element into physical address, and then a second time, once it has the physical address, to store data, the value 0 in the array element in RAM. Okay, so move instruction from start till end will access RAM 4 times, twice to read the move instruction, once for page table and once for reading the instruction, and twice again to write data into array element, again once to get the physical frame number of the array from the page table, and second time to actually write data into array element. Okay, so that's showing you the double accesses that paging has to do to execute these instructions. Okay. Similarly, increment, it will only be fetched. It does not access memory during its execution. So again, when it will be fetched, memory will be accessed twice. Once to get the physical frame number for the increment instruction, virtual address, and then once we have converted the virtual address into physical address, we'll actually go ahead and access the code segment to read the increment instruction. Similarly, it will be done for compare and same thing for jump. Okay, so this will tell you how many times RAM will be accessed during one iteration of this loop. Okay, and this is second iteration, third, fourth, fifth iteration. So again, we are seeing that we have to access RAM twice, whether we have to fetch the instruction or whether we have to read or write data during the execution of that instruction. So this is the thing that was explained in the previous slides, that RAM is accessed twice for each memory access during when we use paging. Okay, and this will make the execution of our programs very slow, because as you know, RAM access is very expensive and very slow, and accessing RAM twice would again reduce the speed of our programs by a factor of 2. Okay, so this is the end of this chapter. Basically, paging solved our problem of external fragmentation, but it came with its two own problems. One, it executes the execution is very slow, and secondly, page tables are big and they take a lot of space. And the next chapter basically explains how these things are circumvented or a workaround. So let me unshare this screen and share the slide for screen for next chapter.
हाँ सही है, हाँ बहुत बड़ा है। मुझे देंगे और एक शायद ठीक है, वो काट के ना वो तकरीबन 6 फुट 6 से नहीं इतना नहीं चाहिए, बस ठीक है, इतना हो जाए नॉर्मल क्लास में। ठीक है ये तो कम से कम यहाँ तक होना चाहिए। अगर यहाँ पे कैमरा फिक्स होना तब भी आप कैमरा रखूंगी फिर इधर लगाऊंगी। अभी मैंने यूज करी नेक्स्ट क्लास में अच्छा, तो वो भी जरा ठीक है व्यवस्थित करना। ठीक है अगले दो से तो नहीं हूँ ना, तो मेरे बात कर। हाँ वैसे उनको याद है।
Okay, so how can we basically find a workaround around this problem of paging, which is that paging makes us RAM access twice and makes the execution of our programs very slow. So the answer is that have you guys read about caches, how caches work in computer architecture or some other related subject? Because RAM access is slow, so we implement caches in our processors. What is the principle that caches operate on? I mean, there's a principle of locality. If you guys, I don't know whether you guys have read or not. There are two types of localities in our programs: temporal locality and spatial locality. Write it here in chat. Okay, if you haven't studied, then I'll just explain it briefly, and you guys can. Mic not working. Okay, no problem. So I'll explain it briefly, but you guys have to like catch up on it offline. Okay. So, but I'll just explain briefly. RAM access is very slow. Okay, because RAM is off chip. RAM is not inside the processor. RAM is outside the processor on another chip. So RAM access is slow. So what the writers or the fabricators of the processors, they observe that our program, when it executes, it does not need all its data all the time. Okay? At any given moment, our program will be executing only in one part of the code. Okay? So it needs only code and data related to only that part of the code. Okay? Your code, total code might have 100,000 instructions, but any given time, your program is inside a portion of the program, inside a loop or inside a function, and it is at that particular moment, it is only concerned with, and it only needs the code and data for that particular loop or function. Okay, the others it does not need immediately. So the principle of caches is that this principle that program needs only local data, local code at any given time is called principle of locality. Okay? And there are two types of locality: temporal locality and spatial locality. Temporal locality says that if we have accessed a data recently, we will most probably access it again in time. Okay, so temporal means in time. If we have accessed some data recently, we will most probably need to access it again immediately. Okay? Just like if you take a loop, the loop iterator I, when you access it in one iteration, you will access it in the next iteration also. Okay, and in the next iteration also. So this data I, it is being accessed, it has been accessed recently, and it will also be accessed again in time very soon. So this is temporal locality. The other is spatial locality. Spatial locality, spatial relates to space, okay, memory space. So let's say the spatial locality says that if we have accessed some data right now, most probably we will be accessing the data around this data, the data near this particular data in memory space soon. Okay. The particular example, typical example for this spatial locality is access to an array. When you access the array element AI, most probably you will access the array element AI plus 1 soon, or AI plus 2, you will access it soon. Okay. So we have accessed array I, and we will access the data around it, in memory space soon again. Okay? We'll need it soon again. So this is the principle of spatial locality. So temporal and spatial locality says that you don't need all the data all the time. It's just that most recently accessed data will be accessed in time again soon. And if we have accessed some data in memory space, most probably we will accessing the data around it soon as well. So caches are built on that principle that we do not need all the RAM all the time. We need only this temporal and spatial locality data immediately. Okay. So inside the processor, we built a small memory, and we call it a cache. And that cache basically contains the data that has been recently accessed and the data which is around the data which has been recently accessed in RAM. Okay. So since our programs operate on this temporal and spatial locality principles, if the data that we have recently accessed is inside the cache, next time we need that data, we don't have to go all the way to the RAM again. We find our required data in cache, and cache access is much quicker than RAM access. Similarly, based on spatial locality, if we have accessed some data array I element in loop iteration 1 and loop iteration 2, we need the array data AI plus 1. Again, due to spatial locality, we will be able to find that data in cache. Okay. So this temporal and spatial locality principle is used in general caches also, and it is again used in accessing page tables also. Okay? So since we are accessing an array inside a loop, so most probably we will be accessing all the elements of the array. So we will be accessing this page table entry which is related to this array in all the iteration of the loop. Okay, so we will be accessing this page table entry very frequently. Okay, so it makes sense to not go all the way to access this page table entry in RAM all the time, but create a special type of memory in RAM, inside the processor, where we can store temporarily this frequently accessed page table entry. Okay, so this is again, this temporal locality principle is used to improve the performance of page tables also, because once we have accessed a page table entry for the first time, let's say we have to go to RAM to access that page table, but once we have accessed it, we will basically bring it and store it in our cache inside the processor. Okay, so next time we need to access this page table entry, we do not need to go to the RAM, but we will find it in our cache inside the processor, and we will access it very quickly, and we will avoid one trip to RAM. Okay, so the caches that we have inside the processor, inside the MMU, to store page table entries, we call them TLBs, or translation look aside buffers. Okay, so paging was very slow. So what we can do is that we can store the frequently accessed page table entries inside the cache, so that we don't have to access RAM twice for every memory access. The page table, we'll find it in the cache, the page table entry, and we'll save one trip to RAM that was for the page table, and we can convert the virtual address into physical address very quickly, and then to access our actual data in RAM, we'll go and access the RAM. Okay, so we'll access with page table, this TLBs, which are caches for page table entries. If we are lucky, then we will be accessing RAM only once. Okay, so this is again accomplished via hardware support. TLB, translation look aside buffer, is a cache for frequently accessed page table entries for frequently performed virtual address to physical address translation. We store those frequently accessed page table entries inside this cache. Okay, TLB, it is part of MMU. So when we have a virtual address, we need to convert it into a physical address. So first of all, we will try to find its page table entry inside the TLB. Okay. If we find it inside TLB, it's called a TLB hit, and we can quickly convert this virtual address to physical address. Okay, and if we don't find it inside a TLB, then we go and access the page table in RAM. We read its page table entry, and we will basically, after reading this page table entry, the physical frame number, we will update our TLB to store this physical frame number or page table entry inside the TLB, so that this time we didn't find it in TLB, but for the next iterations or next accesses, we will be able to find it inside the TLB. Okay, so when there's a TLB hit, we find the frame number directly inside the TLB cache, and we don't have to go to RAM to access the page table. Okay, when there is a TLB miss, then we do have to go to physical RAM to access the page table. So for that particular access, we will have to access RAM twice. But once we read the physical frame number from the page table, we'll also update our TLB to store this page table entry in RAM, in the TLB cache, so that for next accesses, we don't have to access page table in RAM. Okay, so we use this hardware support to speed up paging, so that we don't have to access RAM twice for every memory access. Okay, all the memory accesses where there's a TLB hit, RAM will be accessed only once to read the actual data. Okay? But all the accesses where there's a TLB miss, then we do have to RAM access twice, once to access the page table and second to read the actual data. But due to temporal and spatial locality, we are assured that TLB misses ratio will be very, very low compared to TLB hit. Okay, is it clear what is a TLB and how does it improve the caching performance by using the principles of temporal and spatial locality?
Yes, sir.
And to others? As I said, you might have to, for those who are not here or who did not get what temporal or spatial locality is and how does it help to uh, improve cache performance by using hardware caches as TLBs. You might have to do some background reading on what is a temporal and spatial locality, how does it work, and how do TLBs improve performance. Okay? And reading these book chapters will also help you a lot. These book, as I think I have already mentioned it a couple of times at the start of this course, that this book is very, very well written, and it's written in a very student-friendly way. If you guys read this book, I am sure that a lot of things that you do not understand, a lot of questions that you guys have will be answered. And if there are still questions, you can always contact me. So TLB is a hardware cache for frequently used page table entries and which basically improves our cache paging performance by saving us some trips to RAM to access page tables. So here is the MMU hardware circuit which written in pseudocode form is like this, that the MMU receives the virtual address, it extracts the virtual page number from the virtual address, and then it tries to find the physical frame number in a TLB first. Okay? So if it's a TLB hit, we find the physical frame number in TLB, then it's a very good thing. Okay, so we don't need to go to RAM to access frame number because we've already found the physical frame number from the TLB. Okay, so if TLB lookup is a success, then we directly convert the virtual address into physical address by a frame number that we just found, and we access memory to read the actual data. Okay, so we access memory only once in the best case scenario. But if the virtual page number is not found in the TLB lookup is a failure, it's a TLB miss, then we go and access memory to read the page table. Okay, so we read the page table to extract the physical frame number from the page table and the page table entry, and we write this page table entry into TLB so that we can access it the next time. Okay, so it will update the TLB with the new physical frame number that we found in a page table. So this is one access to RAM in a TLB miss. We access RAM once to access the page table to get the page table entry and write it in the TLB, and then we restart the instruction, which basically again generates the virtual address and the virtual page number, and we look it up again in the TLB. So this time we will find it in the TLB because we just updated it a few cycles ago. Okay? So we will find this virtual page number in the TLB, and then we can access RAM, convert it into physical address to access RAM to read the actual data. Okay? So in case of a TLB miss, we had two memory accesses. Once to read the page table, to get the physical frame number and update the TLB, and then from the TLB we read this page table entry and convert the virtual address physical address and then access memory to read our physical data. Okay? The key thing here is that okay, one is that in case of a TLB hit, we need to access RAM only once to read our actual data. In case of TLB miss, we do have to access RAM twice, once to get the page table entry from page table in RAM and update the TLB, and then after converting the virtual address to physical address, then a second time to read the actual data. Okay? And the key insight here is that due to temporal and spatial locality, the percentages of TLB hit are much higher than TLB miss. Okay, that's why it's a win-win situation for us. Most of the time we will be accessing RAM only once, even with paging. But for this we need this hardware support in the form of TLB caches for frequently accessed TLB page table entries. So this is an example. How much time do we left? We still have a few minutes. So let's say we have 8-bit address space, which means we have 256 bytes of memory and 16-byte pages. And we have an array of integers, which is 4 bytes each. So this is our virtual address space of 256 bytes. Each address is of 8 bits. And we have these 16 pages, and each page is of 16 bytes. Okay? Each page is of 16 bytes, and there are 16 pages in total. So when we allocate memory for an array of 10 integers, let's say it is allocated like this inside the virtual address space. Okay? So it is covering 3 pages, virtual pages, page 6, page 7, and page 8. So these pages will be stored somewhere in physical RAM. Okay? And in page frames, page 6 will be stored in, let's say, physical frame X, 7 will be stored in physical frame Y, and 8 will be stored in physical frame Z. So when we access these array entries, our instruction will generate virtual addresses of A0, A1, A2, etc. We have to convert these addresses into physical address to actually get their data from the physical page frame in RAM. So let's say when the program starts, the page table is in RAM and TLB is a cache in MMU on the processor, which is empty, and the program asks you to read the value of A0. So following this algorithm that we Okay, I was disconnected. I don't know by whom, but okay. So I was asking a question that if we have a situation like this address space with 16 pages, each of 16 bytes, and we declare an array of 10 integers, which is placed like this in these 3 pages, and start of our program, the page table is in RAM, TLB cache is empty, and the program asks you, the processor asks you, you are the MMU, to read the value in array element A0. So how many times will we have to access RAM? Any response, please?
Sir, can you please repeat the question?
My question is that we have this situation, this address space, virtual address space, and we have allocated an array of 10 integers in our program, and these three pages have been assigned 6, 7, 8, and the array is allocated like this in these three pages. So these are virtual pages and virtual addresses. Now you have to play the role of the MMU. The processor gives you the virtual address of array element A0. So you are the MMU, you have to get the value from the physical address for this array element A0. Okay, and the assumptions are that the page table is in RAM and the TLB cache is empty. So to read the value of array element A0, how many times will you have to access the RAM? Based on our
Twice.
discussion, very good. Why twice?
Sir, because the TLB is empty, so when we will first get the physical um page
The
number of
frame number, the frame number.
frame number, yes, of A0, and then we'll also save it to TLB as well, and then we'll access the actual data.
Very good, very good. Okay, so for the A0, we will access RAM twice, and immediately after that, the processor asks you to read the value of A1.
Then one, I guess it'll be one.
Very good. It will be 1 because for the page frame number, we don't have to go to RAM now because page frame number we will find it in TLB now. Okay. Very good. And for A2,
One.
good. And for A3,
I think twice.
very good,
But
because this entry is not in TLB, so it will be updated now. So for A3, we'll access twice, and for A4,
once,
once, A5,
once,
A6,
once,
A7,
then twice,
very good, A8,
once,
A9,
once.
once. Okay, very good. So you see, there were like 3 TLB misses out of 10. So we had 70% TLB hit rate and 30% TLB miss rate. And I'm sure you guys can see that if the page size is big, then here we had a page of only 16 bytes. Okay, it's very small page. But if the page size is big, then our hit rate will increase. Can you guys see this?
Yes, sir.
Very good, because for every page we miss only once. Okay, so the bigger our page size is, the bigger our hit rate will be. Okay, so due to locality, we'll assure that the hit rate will always be much higher than TLB miss rate. Okay, so even with paging, we will be accessing RAM only once, thanks to TLB cache. So here it's the same thing that we just discussed. Okay, so with page size, it would increase. So the other thing is how the TLB miss is handled. Okay, so there are two types of philosophies to make processor architectures. One is CISC, called complex instruction computer, and the other is RISC. Okay. I'm not going into the detail if you guys don't know, but the principle here is that CISC have complex hardware and the RISCs have simple hardware, okay, the processor circuits. So when there's a TLB miss, we need to go access the page table in RAM and update the TLB. Okay. So who handles this process? Who handles this TLB miss, and who handles this updating of the TLB? Is it the software or the hardware? Is it done in software or hardware? So the simple answer is CISC can afford to have complex hardware. So in CISC, it is done in hardware. The reading the frame number from RAM and updating the TLB is done by the hardware, and in RISC, this is done by the software. Okay. Whenever there is a TLB miss, an exception is generated to tell the OS, and then the OS code reads the PFN from the frame page table in RAM and then updates the TLB. Okay. So this is this, and okay, so TLB again is the cache. It contains this frequently accessed page table entries. It contains a mapping from page virtual page number to physical frame number, and plus some extra bits for validity, protection, etc. So I expect you guys to go ahead and read this thing in the book, because the time now is ending, and I will also try to upload a video for this last few slides. Okay, whatever we have discussed, like until this array, this we have discussed, and I expect you guys to read it up in the book, and if you have questions you can ask me. For the rest of the slides, I'll make a video and upload it on YouTube. So if you guys have any questions right now. No? Okay, so if there are no questions, then thank you very much, and you guys can mark your attendance here by writing your name and registration number, and I'll extend the deadline of the assignment till Sunday. Okay. So thank you very much, and please start reading the book. I'll disconnect now. Stop the recording and disconnect now.